Hello, everyone. Let's begin by an overview of multiscale phenomenon in mechanical systems. These are some of the books that we can follow during the course, especially the first one, Fundamentals of Multiscale Modeling of Structured Materials, might be useful. I have provided the links in the slide below. So before we talk about the multiscale modeling, it's important to understand what is a model. A model is a simplified representation to analyze reality or understand the reality and the real world phenomenon. What's the purpose of a model? So a model can be used to simulate complex phenomenon or system or illustrate specific aspects of real world, or it can also help in making decisions for a particular research, development, or policy making or educational purposes. There are different types of models. There can be physical models such as a globe for world or map. It can be architectural models. There can be mathematical models, such as that is used for physics or economical or engineering applications. There can be statistical models, such as linear regression or machine learning model. There can be conceptual models, such as diagrams or flowcharts that are used in biology. And there can be computational models, such as algorithms, simulations, such as climate model, atomistic simulation model, which we're going to talk about in the following lectures and so on. So there can be different types of models, and we are particularly focusing on computational models. When you talk about multi-scale modeling for mechanical systems, it can encompass a lot of different aspects. So for example, it can consist of atomic structure, molecular structure, mesoscale structure of finite element structure. But the overarching goal is to integrate modeling at different spatial and temporal scales so that we can emulate the real scale phenomenon and we don't have to do experiments over and over and to save computational cost as well as experimental cost. When we talk about quantum mechanical phenomenon, it can talk about subatomic particles such as electrons, protons, neutrons, and so on. And especially electrons are of special interest. And there are various methods to solve quantum mechanical phenomenon for electrons. One of the most popular are density functional theory. So there are different software again to implement this density functional theory, such as Quantum Espresso, VASP, GPaw, Avenir, and so on. Now we move on to higher scale, higher length scale. So these can consist of molecular dynamics, where instead of looking at electrons, we can look at system which consists of several electrons in an atom or atoms. And there, instead of dealing with quantum mechanical principles, we'll deal with classical mechanical or Newton mechanical principles. So using those, we'll be dealing with molecular dynamics, force field simulations. And some of the softwares that are used for these molecular dynamic simulations are LAMMPS, GROMACS, GULP, and some other like ASC. While quantum mechanical principles are used for quantities at very low length scale and used for very fundamental quantities such as elastic constants, Poisson ratio, and so on, molecular dynamics simulation can be used for very large systems such as still like 10,000 atoms and so on, which is still can be useful for various types of material, that is our metal, polymers, ceramics, and so on. Now we can go beyond the molecular dynamic simulations and we can group number of atoms. So this is also something called coarse grain modeling or microstructural modeling, where instead of looking at atoms together, we are looking at the collection of atoms, and that what leads to phase field or microstructural models. Some of the softwares for this is Damask, Moose, Prism FF, PF, and so on. Now we can go beyond that as well, and we can look at elements instead of atomic structure or electronic structure. So this is useful for studying such as deformation, heat transfer, using finite element model, and also can be used for something like computational fluid dynamics. So these are some of the softwares that can be useful, such as ANSYS, PPI, Phoenix, and so on. So this is just an overview and introduction. During the course, we'll be going through some really detailed key principles behind these different methods, and also we'll go through hands-on session that will be useful for engineering applications. Now, this This is an overview of different length and time scale simulation methods. We'll be seeing a lot of pictures like this in internet, where we deal with mesoscale, microscale, and a continuum scale method phenomenon. So at quantum level, we can have uh, solving density functional theory or ab initio method, where we will be dealing with the Schrodinger equations, or we can go beyond this femtosecond or nanometer range and deal with picosecond and micrometer range using atomistic modeling, which uses the Newton's principle. Or we can go beyond that and look into micrometer or millimeter range using coarse grain modeling using mesoscale for polymers, dissipative particle dynamics, and so on. Or we can go beyond that and study using finite element simulation heat transfer methods. So you can see multiscale modeling has the advantage of studying um, uh, mechanical principles at different length scale as well as different time scales. And depending on the problem that you are trying to solve, you might use one or a combination of multiple of these methods. You'll see different types of this picture or this plot in different books. So this is one type of representation that is adapted from this multi-scale modeling book, but there can be other similar plots where we have DFT, MD, dislocation dynamics, crystal plasticity, and so on, and where one model is feeding to other model. The information from one model is feeding to another model, such as even density functional theory. We can use machine learning interatomic potentials to feed to molecular dynamics and run temperature-dependent phenomenon and large-scale phenomenon. So DFT is usually used for 0 Kelvin calculations, but here we can see that it can be used for high temperature and large-scale simulation as well. The information from the molecular dynamics can be fed back to dislocation dynamics and back and forth, that is atomistic to continuum level methods. And then this can be fed to using homogenization technique, the crystal elastoplasticity models. And these are some of the approximate length and time scale that are used for certain modelings. Now, what is a multiscale modeling? A multiscale modeling is basically very simple, where we combine different methods that we learned at different length and time scale methods and to solve a particular problem, especially for mechanical system. So here in this example, we see a molecule simulated with molecular dynamics, or a crack propagation example using FEM or finite element methods. So traditional approaches such as DFT or MD by itself can focus on single scale, but may fail to capture complete picture of a mechanical engineering problem. And this is why we need multi-scale modeling. So multi-scale modeling can provide more comprehensive understanding of the phenomenon at different scale, and can be more accurate because it is not looking at only one scale, but at different scales. So what are the challenges of multi-scale modeling? As you can see here, computational complexity. So as we are dealing with significant computational resource requirements at different scales, such as quantum, classical, and so on, it can be extremely complex. And bridging different modeling methods, such as the from DFT to MD, from MD to mesoscale, from mesoscale to finite element, how to pass information from one type of method to another type of method, what's the boundary level problem, what are the challenges. This can lead to different complexity in bridging the different scales in length and time. Also, the most critical part is how do you validate whether our model is working? So you always have to validate our model against experimental data wherever applicable to make sure that these models actually make sense. So this part is critical, and it's hard to find good benchmark data for validating our model. Now, finally, data integration. We have to integrate data from different sources and scales to make something which is a more cohesive model for a complex process. So that is extremely critical. For example, in this animation, you see a car collision to a wall. So when a car collides to an object, you can model the entire thing as using finite element model, but Then you might also need for certain application, such as you want to find better alloy, you want to go at molecular dynamics or atomistic scale to find at elemental or chemistry level, how does that affect the global finite element simulation. So for example, you can take the bulk modulus or elastic constant from quantum mechanical principle or atomistic level calculation and feed back to mesoscale or finite element simulation to see how does an alloy will perform when a car collide to a wall. Of course, if you have only iron-based alloy versus iron and cobalt-based alloy, they might have different response. So you see, all these methods are kind of interconnected. And it's very difficult to kind of capture the scale bridging and how to validate these models over different phenomena. So we can use this challenge as opportunity. So we can use this as a material design opportunity for multi-scale modeling, and which offers the potential to design materials with tailored properties and manipulate behavior at different scales. We can also use predictive modeling to improve predictive capabilities of multi-scale models that can lead to better informed decisions in the design and analysis of mechanical systems. Or we can lead to different innovation opportunities. So we can look for accurate model or better materials that can solve some of the mechanical engineering problems. Or it can lead to interdisciplinary collaboration, because these multi-scale modeling requires information from material science, physics, computer science, chemistry, and it leads to obvious opportunity for collaboration across different disciplines. So now I will list some of the laws or principle that you might have already familiar from your undergrad or grad level courses, but I just list there just to be familiar with, and that will be used for a remainder of the course. So for example, Newton's laws of motions might be an obvious one. For the example, the first law, the law of inertia. Second law is the force and acceleration. One of the key principles is force is proportional to acceleration, where the proportionally constant is mass here. Or you can have third law of motion, a third law of action and reaction, and so on. Similarly, we can very critical or very important is the conservation laws. So conservation of energy, where the total energy of isolation system is always constant. Energy can be transformed from one form to another, but cannot be created or destroyed. It's an important conservation of energy. Of course, there can be certain violation or there can be issues, but for mechanical engineering applications, if you're not going to particle physics and so on, I think it's good to conserve energy for a system. Also, you want to conserve mass. So for example, if you're dealing with fluid flow or heat transfer and so on, we want to make sure the mass of a closed system remains constant over time. Also, we want to conserve momentum. So the momentum is usually mass into velocity. So you want to make sure the total linear momentum of a closed system is constant unless acted upon by external forces. So these are extremely critical or extremely important laws that are used for mechanical engineering applications. There are also other laws such as thermodynamical laws, first law, second law, and third law of thermodynamics. So the first law says that the change in internal energy of a closed system is equal to the amount of heat supplied. So it's kind of the related to the conservation of energy law. Second law of thermodynamics, where heat cannot spontaneous flow from colder location to hotter location. This is kind of entropy argument. Or third law, whereas it says as a temperature approaches absolute zero, the entropy of a system approaches a constant minimum. Some of the other mechanical principles are Bernoulli equation, continuity equation, and Navier-Stokes equation. So these are important because we'll be solving some of these problems for computational fluid dynamics. So I have just listed here, for example, the continuity equation is extremely important. A1, B1 is A2, V2, where it says that the area and cross-sectional area and the fluid velocity, for example, if you take a pipe and one has a small nozzle and one have a bigger nozzle, so the area might change. So accordingly, the velocity has to be changed. So that's continuity equation. So there's fluid mechanics. Similarly, heat transfer law. The heat transfer law, Fourier's law of heat conduction, extremely popular. where it says the time rate of heat transfer through a material is proportional to the negative gradient in the temperature and the area through which the heat is flowing. We are going to work with some of these laws and equations so that you'll have better hands on these laws and actually apply it for engineering applications. Similarly, Stephen-Boltzmann law and Newton's law of cooling are important. In material science, of special interest is Hooke's law, where it says that the stress proportional to strain, given by a proportionally constant called Young's modulus. This is especially applicable for linear elasticity. Now, if you go beyond linear elasticity, you might have to consider like yield criteria, von Mises criterion, and for which we have to study the plastic deformation. Finally, the kinematics and dynamics equations, such as the velocity, establishing the relationship between initial velocity, final velocity, time, and acceleration, displacement, and so on. So, for example, the final velocity v is given by the initial velocity with added acceleration and time. Similarly, displacement is given by ut plus half at squared and so on. So this might be useful, not really necessary, but can be useful for mechanical engineering application. So what are the key concepts in multiscale modeling? First, you have to understand time and length scale. So you have to find out what is the problem you are trying to solve, and based on that, you have to identify the particular method that you're going to work with. When you have multi-scale modeling, such as from DF2 to MD or MD to continuum, so on, you have to understand how to link the models at different scales and ensure that information is correctly transferred between them. So, for example, if you're trying to simulate a collision of a car, you want to make sure that you model the material with the particular material parameter, but also use particular boundary conditions and so on to kind of couple the different length scale methods. Also, there are certain concepts of homogenization, or such as where we have to derive effective properties at a large scale based on the behavior of a system at a smaller scale. So we want to be consistent, which also relate to the coupling mechanism. Heterogeneity is basically recognition that material properties may vary across different regions of system, across affecting its overall behavior. So it's saying that at different scale of length and time, a material may behave differently. So these are some of the slides for this module.